Okay, now we're going to go through the individual processes. The order here doesn't really matter. The first one is isochoric. This is a constant volume process. So how you can think about that is having a gas in a fixed volume container. There's no way for the volume to change. What that means is if the temperature increases, because you've heated it, since the volume has remained the same, the pressure must have increased. What this looks like on a PV diagram is a vertical line. You have the same initial and final volume, but your pressure has changed. So isochoric is one of the simpler processes to think about, since when you have PV equals nRT, you see that if V is fixed, P and T will just be proportional. Isobaric, I think it can be a tricky name to keep in mind. How I remember it is that we talk about barometric, which sounds like baric, pressure. So isobaric refers to pressure. And in this case, the volume is allowed to change, but the pressure is fixed. And again, the reason how we think about pressure here is that there's a mass pushing down on the gas. And in this picture, we're thinking about the mass of the piston alone. So initially, the piston is not accelerating. This means it's in equilibrium. Therefore, the force pushing down is equal to the force pushing up. Well, what force is pushing up? That's the pressure times the area of the gas. So you have two forces in equilibrium here, and then you have two forces in equilibrium here. Well, since your mass of the piston hasn't changed, that means the gravitational force from the piston down hasn't changed. So the only way these both can be in equilibrium, since the piston isn't accelerating, is if the pressure of the gas times the area is equal in magnitude to the weight of the piston. So that's how we think about pressure being maintained in this process. So pressure is maintained, which means that we have a horizontal line. And then we have two different volumes. So again, we know that temperature has changed since there's no way for these 2 points to lie on the same hyperbola. So that's one of the ways that it's helpful to think about the isotherms, is to recognize that even though we haven't labeled a change in temperature here, there must have been a change in temperature. So constant pressure means that you do have a change in volume. Isothermal, it's easy to see that the name means the same temperature since therm is right there. And you can think of this as basically fixing your object to be in a constant temperature bath, right? So imagine that this is in the ocean and that the ocean all has the same temperature. Clearly, there's no way that this is going to come out of thermal equilibrium with the ocean. So you could also imagine maybe having a little thermometer here that turns on a heater or turns on a cooler if the temperature changed at all. But so we are fixing the temperature to be the same. And what we can do is actually give a push. And now this doesn't necessarily show that the push is still there or not, but we've changed the pressure of the gas. We have also changed the volume of the gas. So that's where we have to think about there needing to be some sort of push involved here, since my initial pressure and my final pressure are different. And at least in the direction we're going here, my initial pressure is lower than my final pressure. So that's like saying initially I only have my piston there, but then I give it a push to get it here, but then I have some push that stays. So this could be adding masses or something. We are actually changing the pressure throughout this, so we're not going to be too worried about the details of this push, but there has to be some change in downward force to create a change in pressure. But we also have a change in volume. So in this case, the temperature is fixed, and this is along one of our isotherms. So if you have an isothermal process, either going from a larger volume to a smaller volume, or vice versa, you know that the pressure must be going the opposite direction. So bigger volume to smaller volume means smaller pressure to higher pressure for the temperature to stay the same. But again, for each of these processes, that we have to have done something to actually make sure that the temperature stays the same. So always think that we have to really define these processes very carefully. And this is going to give you a hyperbola. Okay. I want to cover the adiabatic process here because I think it's really helpful to realize that there are 4 special processes. However, the adiabatic process is not introduced in Chapter 8, it's introduced in Chapter 9. The adiabatic process might be the hardest one to think about, but in many situations is the most important. So briefly, this will come back in Chapter 9. An adiabatic process, it occurs when something is well insulated or the process is so fast that you don't have any heat entering or leaving, so no heat is exchanged. That is the definition of an adiabatic process. However, work is done. Now again, we haven't quite defined this yet, but that's also important to know for an adiabatic process. We see that the temperature changes and the pressure changes, which the volume changing is actually directly related to work being done. So all 3 of our state variables change. So the adiabatic process follows this shape called adiabats, and the definition of this shape is kind of confusing. It's a curve, but it's not the same curve as an isotherm, which shows you that the temperature itself is changing. So the pressure, the volume, and the temperature change in an adiabatic process, but what's defining it is that no heat is exchanged. So we'll come back to this much more in Chapter 19, but it's important as you're learning these processes to know that there's this 4th one, because it is essential. Lastly, you should know that in many times we're going to have a process that actually has multiple steps. So you need to identify the specific process for each step and then relate them together. So for instance, we can have a process where we take the gas from state 1 to state 2 to state 3. You see that there's actually 2 different individual processes that have occurred. So what's helpful is that we can talk about what happened from, for instance, state 1 to state 2. That lies on an isotherm. So it's an isothermal expansion because it went from a smaller volume to a bigger volume. But now, because we know that that's isothermal, we can define what the pressure is. Then we compress it isobarically from state 2 to state 3, and in this case we're changing the temperature and we're changing the volume, but we know we're not changing the pressure. So frequently we're going to have multiple steps like this, and you need to actually set up equations, really being clear with your notation, saying how your volumes, pressures, and temperatures relate to one another, since the final state variables of one process are going to be the initial state variables of your next process. This is going to be very important for cycles, which in a way is the whole point of thermodynamics. Eventually we get to the idea of refrigerators and engines, and we learn about efficiency, and this is really helpful for thinking about why we can't make perfectly efficient equipment, why we can't actually have perfectly efficient cycles. So putting multiple processes together is going to be something that we do in future sections and future chapters. So please always be careful with your notation and get ready for multi-stage processes.